Okay, now I want to switch gears to talking about drag. So if instead of moving through a vacuum, we're moving through air or some fluid, then there is a force of air resistance or drag that opposes the motion. And how does it know what direction to point itself in? It looks at the velocity and goes in the opposite direction. And so you can think about this force as the fluid has to flow over the sphere, different layers of fluid have to slide with respect to one another. And that sliding entails a bit of friction. And that friction produces this drag or loss on the particle. Stokes' formula for a sphere gives you the force in terms of the viscosity, which is just some property of the fluid, the size of the particle, the sphere, the radius, and the speed v at which it's trying to move through the fluid. Now, why is it nice that this is proportional to v? What should happen if v goes to 0? There shouldn't need to be any friction if it's not trying to move. So that's good. Of course, any power of v might have done the trick, at least if it's positive. And then this coefficient of viscosity is just some fudge factor that we could measure empirically. It might depend, it certainly might depend on the fluid. It might depend on the temperature. It might depend on, well, if it depends on the velocity, then we have a problem with this expression, because the expression is pulling out the velocity dependence explicitly. So, so for small velocities, this is the expression for the force of drag. And now I'd like you to tell me, what are the dimensions of viscosity?